In this video, we're going to look at calculating our estimated regression equation. But before we do that, there is one thing that I want us to talk about. So looking at this graph, right, this represents a couple of different regressions. Right? We're going to be calculating our regression equation where we need to know, well, what makes a good regression equation. Right, looking at all of these, right? So here we have our data in black. Those are the black dots, right? And then we have three proposed regressions. So which one should we select, right? Well, starting with C, probably don't want that one. It seems to be has a different slope. This data seems to be sloping upwards. And C is sloping downwards. It's probably not a great sign, probably going to tell us that we're not going to have a lot of success with that one. Then moving on to A, we can see that while it does have the slope right, at least, it doesn't go through much of the data. It's not very close to a lot of those data points. And when we compare it to B, which runs through the middle of the data, is very close to more of those values, we can see that B would be the better choice, right? The line, right, the regression that is closest to the data is the best, right? Regressions are designed to predict, right? We want to be able to take an X value and predict a Y. So the one that can make the best predictions is going to be the one we want to choose. And we know that the error is the difference between the observed value and the predicted value. So the smaller that is, the better our line fits the data. So just writing that out, our error, right, our error term, we could even throw some I's on there if we wanted to. Our error term is just the difference between the observed value and the predicted value. We can write this in slightly more mathematical terms. As EI equals yi, so this is the observed value minus yi hat, which is of course the predicted value. So by finding the equation, the regression model that has the lowest error term, we can find the one that fits the best. All right, we run into some similar problems that we've seen in the past in this class and also in Stats 1. If we calculate all of these errors, some of them are going to be positive, some of them are going to be negative. And if we just try to add them up and take the average, they're going to cancel each other out. So we're going to do what we often do in this situation, and we're going to square our errors. So our sum of squared errors, or SSE, this should look somewhat familiar from the last chapter, ANOVA. The sum of squared errors is equal to the sum of yi minus yi hat squared, right? So nothing too terribly shocking, right? So these are our errors. We're going to square them and sum them. So we squared them, now we're summing them. That is what our sum of squared errors are. We'd also write it as the sum of the actual error, write out that actual error value. So the sum of EI squared. So again, the line that has the smallest sum of squares error is going to be the best fit. And we call this line the least squares line. All right, so we want the line, we want that least squares line. So the version of regression that we're going to be doing is what's known as ordinary least squares, or OLS. So you can kind of think of OLS as kind of the basic starter version of regression. There are many additions and changes and kind of adaptations to meet different problems that you might come up when you're trying to model some relationship. But we're going to keep it relatively simple. We're just going to stick with that ordinary least squares for now. So here are what we're really doing with these ordinary least squares. We're just trying to calculate B0 and B1, right? Y hat, that's going to come when we start predicting, start plugging in values in our regression equation. Xi, that's going to just come from the data that we've collected. So we're going to try to figure those out. So when we start to calculate a regression equation, we're going to have to start with B1. The reason for this, as we're going to see shortly, is because B1 is in the formula for B0, so we can't really find B0 without finding B1 first. All right, and here is our formula. Okay, so our formula for V1 is N, which is our sample size, pretty standard, times the sum of Xi times Yi, minus the sum of Xi times the sum of Yi, divided by N times the sum of Xi squared, minus the sum of Xi squared. Right, so just running through these really quick just so we know what we're doing here. All right, sum of Xi, Yi. So when we are doing this, we need to take so in pairs, so kind of for an observation, right? We're gonna, for each observation, whatever we're looking at, we're gonna have a Y and an X, right? And they're gonna be tied to the same observation, same person, same whatever it is, whatever element we're looking at. All right, so we take those two values, we multiply them, set them aside, go down to the next pair, multiply them, set them aside. Once we've multiplied the X and Y together for all of our data, we're gonna then add the product of those up. So add up all those numbers that you just got from multiplication. All right, and that's your sum of Xi times Yi. All right, sum of Xi, sum of Y should be pretty familiar, right? Sum of Xi, you're just adding up all the X's. Yi, just adding up all the Y's. All right, then coming down to the denominator, all right, once again we have N, right, then the sum of Xi squared. So the sum of Xi squared, so this one, sum of Xi squared, this is where we take our X's, we square them, and then once we have squared them, we add them up. Right, so it'd be x1 squared plus x2 squared, so on and so forth. The sum of Xi squared is different, so this one in brackets. Here, right, you can see it is in brackets, right, and the square is outside of that bracket. So here we're gonna add up our X values, just like we did right here. And then once we've got that sum, once we've added those X values together, we're gonna square that sum, all right? So that is an important distinction, all right? But that is how we're gonna calculate B1. And B0 is a little bit easier to calculate. right? B naught equals y bar minus b1 times x bar. So if we've forgotten from chapter 4 and stats 1, where we went over the means, whenever we have that bar, that's a mean. So y bar is the mean of y, x bar is the mean of x. All right, so now let's look at an example. To save space, I'm just going to say kind of what the example is. I'm not going to write it down on the board. But let's say that you want to be able to predict how many hats someone owns given their age. All right, so using their age, how old are you? You tell me, oh, well, now I know how many hats you own, right? We're predicting number of hats owned with age, all right? So this is a silly example, but that is something that we might be looking at. All right, we're going to talk about this in a little bit. All right, so we've got two variables. We've got hats. We've got age. And when we're setting this up, right, when we're setting up our model, right, it's a good idea to go ahead and set up that model, right, where we have our beta naught, beta 1. Right? If we're not told which one we're wanting to predict with, we might have to think it through, right? So if we were just said, calculate a regression using hats and age, right? These are your two variables, number of hats somebody owns, and what their age is, right? And we have to decide which one's gonna be our dependent, which one's gonna be our independent. We wanna think about that causal relationship, right? So for this silly example, it wouldn't make sense for someone's age to be determined by the number of hats you are, right? So if somebody, takes you lose a hat, your age doesn't change, right? So that relationship doesn't make sense, right? But it might make, and it doesn't make a lot of sense, but it's arguably more reasonable that a person's age will determine how many hats they own. Right? Maybe younger people own more hats because they're more interested in I don't know, hats really classify as fashion. I guess they do, depending on the hat. Or maybe older people do because they've had longer, more time to collect hats, right? Whatever the case, right? That's gonna make more sense, right? So when we're setting up this model, and we're deciding on dependent and independent variables, it would make more sense for the dependent variable to be the number of hats owned, which we're gonna use, just hats is gonna be the name of that variable. Right, and the independent variable is age, right? So number of hats is dependent on how old you are. That's kind of what we're setting up. So once we know which one's going to be our independent variable, which one's going to be our dependent variable, we can go ahead and write this model up. Right, so again, if we remember from the beginning of this chapter, our model is where we've got our betas, where we've got the EI, so the little epsilon I or whatever it is, right? And so this is what our model might look like. This is telling us the relationship is that the number of hats somebody owns is determined by or is dependent on this equation, right? And so it's dependent on the age of the person. All right, so that's what our model would look like. Now let's look at actually calculating our estimated equation. Right, to estimate an equation, we're going to have some data. So let's write this up here. we go. So that's our data. Now we can go kind of get to business. All right, so when we're doing this, the way I like to do this, if I'm going to be doing this by hand, I like to just get those sums and just kind of pull them off to the side and then fit them into the equation later. All right, just because of the amount of board space and the amount of erasing and then writing stuff up, again, I would have to do, we're going to just kind of truncate this stuff, or I might like kind of go through how we're going to find some of these, but I'm basically just going to write down the parts. All right, so one of the first things that we might want to go ahead and grab is our sample size, right? If we count all of these values, right, we have 10 pairs, right? So we've got, and by pair I mean observation, right? So hats and age, right? There are 10 rows of data, so our sample size is 10. All right, next we might want to find some of the easier ones, so we might want to just do the simple sum of xi, sum of yi. All right, the sum of xi is going to be 315. And the sum of yi is going to be equal to 115. Right, and so again, just as a reminder, the x is age, right? Y is hats. If you flip those up, your regression equation is going to be completely messed up. You're going to get a totally different answer. All right, so we want to make sure that we've got the right things for x and for y. All right, but there we have those. Then we'll look at the sum of xi, yi. Need a little bit more space than that, I think. Right, and the sum of xi, yi is 3,421. More space for that. All right, and again with that sum of xi, yi. Right, we're just taking each of these pairs, right, multiplying them together, then adding them up, right? So 10 times 27 plus 4 times 35 plus 4 times 38, so on and so forth. And then for the sum of xi squared, that's going to give us 10,069. All right, so now that we've got all of that information, we can go ahead and calculate our B1. All right, I'm gonna erase our data so we can leave this information up here. Get that taken care of. All right, so when we start this calculation, we're gonna go up to our numerator. The first part is n times the sum of xi, yi. So n is 10. The sum of xi times yi is 3,421. Then we're going to subtract from that the sum of xi times the sum of yi. So 315 times 115. And we'll move into our denominator. All right, in our denominator, our first term is 10 times the sum of xi squared. So 10 times 10,069. And then we're going to subtract from that the sum of xi squared. So again, this is the sum of xi. We know that the sum of xi is 315. I guess I don't really need a bracket for that, do I? All right, so we're going to take that sum of 315, the sum of 315, the sum of xi, which is 315, and we're going to square it. All right, once we've got this all laid out, we're going to punch it into our calculator. And we should get a B1 of negative 1.375. Right, so now we have B1, we can look for B naught, and we're really almost done with estimating our equation. All right, so B naught equals the mean of y. We didn't throw this up here, but it's going to be pretty simple, right? The mean is the sum of our y's divided by the sample size, right? Our sample size is 10, which makes it easy. So 115 divided by 10, 11.5 is going to be our y bar. We're going to subtract from that B1 times the mean of x. All right, so again, similar thing, so not 315, 31.5. All right, so we need the mean for x, we need x bar, 315 divided by 10, it's gonna give us 31.5. All right, so y bar 11.5 minus B1, which is B1 times x bar, which gives us negative 1.375 times 31.5. Once we finish our calculation, we're going to get a B naught of 54.812. All right, so now that we've got B1 and B naught, we can actually write out our estimated regression equation. So starting off, we're going to put in our dependent variable. All right, so hat's I, and we want to make sure that we put a hat over it. That hat symbolizes that it's the predicted value, but this is the estimated equation. So hat's I hat. All right, hat's I hat equals B naught, which is 54.812, plus plus B1. B1 in this case is negative, so it'll be minus 1.375 times HI. And because this is the estimated equation, we don't have that error term. Right? That error term is only for the model and not for the actual equation. All right, so let's talk about what all of this means. So really what we're talking about is interpretation. All right, so for B naught, again, that's our y-intercept. And that's going to tell us the average value of y when x is 0. Right? So that's the generic way of interpreting beta naught. For beta 1, the interpretation is that a 1 unit change in our independent variable, or x, is expected to lead to a B1 change in the dependent variable. All right, so we're going to put it in terms of an increase just so it's a little bit more streamlined. right, so a 1 unit increase in X is expected to lead to a B1 unit change in Y. All right, so I put change instead of increase because Y might not actually increase. So it's going to depend on B1. If B1 is positive, then as X increases, then Y will increase. But if it's negative, of course, the opposite will be true. As X increases, Y will decrease. All right, but whatever beta or B1 is, so in this case, in our case, it's negative, so it would be an increase in age leads to a decrease in hats owned, right? That's what we're looking for. Speaking of this example though, let's just go ahead and run through these parameters, right? Or these coefficients. Actually, before we do, one thing to note, most of the time, I'll be honest with you, most of the time we don't really care about B naught. B naught is just there because we need it to be or we want it to be, but we're not going to interpret it that much. It's not going to be that interesting in a lot of cases, especially when we get into the next chapter where we're looking at multiple regression, where we have multiple independent variables. It doesn't make sense and it doesn't really tell you anything. So really the focus here is going to be on B1, but just for the sake of us going through it, we will interpret B naught. All right, so our B naught is 54.812. So the interpretation here would be, right, so it's the average value of Y when X is 0, right? So X in this case is age, so when age is 0, we'd expect the average number of hats someone owns to be 54.812. So again, this is kind of what I mean by they're not always going to make sense. One, not necessarily B naught's fault on this one because this is kind of some kooky data and it doesn't have a super, there's not a lot of variation, which can cause some problems. But you know, it doesn't make sense for a 0-year-old to have 54 hats, right? I don't think. Maybe there is one out there. I kind of doubt that there is. But also, you know, you're not born and are given roughly 54 hats, right? You know, maybe a little bit more, maybe a little bit less because this is an average. But that doesn't really make a whole lot of sense. Not that this regression as a whole makes sense that much. But, all right, but that is how we would interpret B naught in this instance, right? The average number of hats 0-year-olds have is 54.812. All right, moving on to our B1, all right, so this is a 1 unit increase in our independent variable. It's expected to lead to a B1 unit change in our dependent variable, right? So B1 here is negative 1.375. So a 1 year increase in age, so a year, would be expected to lead to a 1.375 decrease in hats, right? That's kind of a weird way to say it, right? Let's see if we can make that make a little bit more sense. I would expect that as a person ages by 1 year, they will decrease the number of hats that they own by 1.375, right? Or the number of hats they own will decrease by 1.375. Right? Either one of those would be acceptable, right? But that's how we're going to interpret those results. As we mentioned earlier, the main purpose of regression equations, regression models, is to allow us to predict the dependent variable. So we want to be able to gather data, calculate our B naught and our B1, and then plug other data into that, right? So if we just know X, then we can find out Y using this equation. So let's look at how we're going to do that. So here we've got the regression equation that we just calculated. Hats I hat equals 54.812 minus 1.375 times age I. So now that we have this, let's say that we wanted to make some predictions, right? Maybe we want to answer this question. How many hats would you expect a 28-year-old to own? All right, so in order to answer that question, it's very simple. All we're going to do is just going to take that 28, that's our age, we're going to plug it into our regression equation where age is, all right, punch that in the calculator, and that's going to give us our prediction. So setting this up, we're going to have hat equals 54.812 minus 1.375 times 28. And that is going to give us 16.312. I almost accidentally wrote 19, but it is 16.312. And it's really as simple as that. That's it. That's how we're going to predict using these regressions. One thing to note though is that if you have transformed data, so if your data is transformed, and by that we mean, if it's, let's say it's currency, let's say we were looking at income, for instance, if income is not in dollars, then you need to be mindful of that, right? So if it's got income in there, but income is in hundreds of dollars or thousands of dollars, and you're told that this individual, you want to predict for somebody with an income of $26,000. If you put 26,000 in there, you're going to get a totally wrong answer, right? Because if the variable you use to predict, so your income, when you're gathering your data, you've got whatever this Y is and your X is income, and that income is in thousands of dollars, then if you don't transform your X that you're using to predict into thousands of dollars, it's going to mess everything up. All right. So we want to be mindful of that. So again, want to know what our variables are. Again, I don't think I said that before, but we do want to know what our variables are. We want to know how they're defined, right? What the units are, so that we can use the appropriate value to make those predictions. All right. Again, if income is in thousands of dollars and you put 26,000 in there, then the regression is going to treat it as 26,000, and it's going to give you a totally different value than you would want, right? What you would want to do is take that 26,000 divided by 1,000, you get 26, so you put 26 in there instead of 26,000. Right? But other than that, that is it for our prediction.